Okay, here we have the test 3 sample problems, and we'll work through these. The first question deals with finding the inverse of a given function and then verifying that the composition in both directions yields the identity. That is, x goes in through each function in turn and comes out unchanged in the end. And the technique for solving this is going to first switch x and y and then solve for y. That's our technique. So we know that this equation is identical to y equals 2 over 3 plus 4x. So if we were to switch x and y, we would get x equals 2 over 3 plus 4y. And we want to solve that for y. This is the correct equation for f inverse, the reflection across the line y equals x. What we want to do is write it as a function, and so to do that we need to solve for y. And we can cross multiply or multiply both sides by the LCD, and we get x times 3 plus 4y is 2, or 3x plus 4xy is 2. Again, remember we're solving for y, so if we leave the y term by itself and divide both sides by the coefficient of y, which in this case is 4x, we get y equals 2 minus 3x over 4x. And that can be written different ways, but it certainly is sufficient. And we have f inverse of x is 2 minus 3x over 4x. Now to verify that that is the inverse, we need to compose it in both directions and show that it yields the identity. Okay, so we'll start with f of f inverse of x, and that would be f of 2 minus 3x over 4x. And if you can see f up here, f says whatever the input is, we're going to take 2 divided by 3 plus 4 times that quantity. And so we have 2 divided by 3 plus 4 times whatever the input was. And let's see, we get some simplifications. The 4's cancel there. And we're left with 2 over 3 plus 2 minus 3x over x. And that can be simplified a bit. 2 over, we can distribute the division. And there's a number of ways of doing this. I'm just doing it one way. We distribute the division. 2 divided by x minus 3x divided by x, we get 2 over x minus 3, and these cancel, and I'm left with 2 over 2 divided by x, and to divide fractions, we know we multiply by the reciprocal, and the 2's cancel, and we're left with x as we expected. Now the composition in the other direction, we're going to want to calculate f inverse of f of x, and that would be f inverse of, well, f of x is 2 over 3 plus 4x, and f inverse we calculated. Where is f inverse? There's f inverse. It takes our input and says that the output will be 2 minus 3 times that quantity over 4 times that quantity. So in our case, we have f inverse applied to this, and we know the result is going to be 2 minus 3 times that quantity over 4 times that quantity. In this case, probably the simplest thing to do after we, for example, multiply 3 over 1 by this fraction, we get 2 minus 6 over 3 plus 4x over 8 over 3 plus 4x is to recognize that we have a complex fraction whose secondary denominators have an LCD of 3 plus 4x, the only denominator in fact. So we're going to multiply top and bottom of our large fraction by 3 plus 4x. 3 plus 4x. And again, implicitly this is over 1. So if you can see that multiplication, it'll have the effect of canceling these secondary denominators. We're going to distribute this multiplication through the numerator, and we get 3 plus 4x times 2 minus, and then when we multiply by the second term in our numerator, the 3 plus 4x is canceled, and we just get minus 6. And here, the entire fraction cancels, and we're left with an 8. So we get 6 plus 8x minus 6 over 8. And the 6 is canceled, and you can see you get 8x over 8, which is x. If you don't get x, something went wrong. All right, so the first problem we've done. The second problem is going to be worked in an identical fashion. Here we have the equation f of x is 2x plus 1 over x minus 3, which is the same as y equals 2x plus 1 over x minus 3. And if we switch x and y, we will have the equation for the reflection across the line y equals x, or the equation of the inverse. It's just not written as a function. Again, it's a very similar technique. Multiply both sides by the LCD, or equivalently cross multiply this times this equals this times this. And we get x times y minus 3 equals 2y plus 1, or xy minus 3x is 2y plus 1. We're solving for y, remember? So I'm going to put my y terms on one side and my non-y terms on the other. And to combine these y terms is equivalent to factoring out what makes them like. And we see we finally get y is 1 plus 3x over x minus 2. And that is our f inverse of x. 1 plus 3x over x minus 2. And again, to verify that this is the inverse, what we're going to do is calculate f inverse of f of x and f of f inverse of x. So we'll start with, say, f of f inverse of x for this guy. So we have f of f inverse of x, working with this one, would be f of 1 plus 3x over x minus 2, which now we can see for the f in question, which is up here, it's twice our input plus 1 over our input minus 3. So we have this large complex fraction, twice our input plus 1 over our input minus 3. And our input in this case is the fraction itself, 1 plus 3x over x minus 2. And we're trying to verify that that yields in the end x itself. So let's see. I guess we'll do the same kind of game. I'll multiply the top and bottom by the LCD of the secondary, these smaller fractions. And again, that's x minus 2, top and bottom. The x minus 2 will distribute over the whole numerator and the denominator, 2 terms and 2 terms. The x minus 2 will come and cancel this, and don't forget the 2. We have 2 times 1 plus 3x plus 1 times x minus 2 over x minus 2 cancels, and we get 1 plus 3x minus 3 times x minus 2. So we get 2 plus 6x plus x minus 2 over 1 plus 3x minus 3x plus 6, which is, let's see, 7x over, let's see, 3x minus 3x over 7, which is x. Okay, so far so good. Now we'll calculate the composition in the other direction, verify that it yields x also. So let's see what we have. We want to calculate f inverse of f of x. So f inverse of f of x. And we're working with these functions. That's f inverse of f of x for part B was 2x plus 1 over x minus 3. And our f inverse of x took the input, tripled it, added 1, and then took the input minus 2. So we have 1 plus 3 times our input over our input minus 2. That's the pattern that f inverse uses. And let's see what we have there. In our case, the input was 2x plus 1 over x minus 3. 2x plus 1 over x minus 3. And again, similar technique. Multiplying top and bottom by the least common denominator of all these second level fractions. So we get x minus 3 times 1 plus, don't forget the 3 here, and then we get 2x plus 1 minus 2 times x minus 3. And so we get x minus 3 plus 6x plus 3 over 2x plus 1 minus 2x plus 6. Again, the 2x is canceled, the minus 3 and plus 3 cancel, and we get 7x over 7, which is x, as we hoped. So, in both cases, we find that the correct F inverse was found. Okay, let's look on to some of these. The second problem here is 4 equations we'd like to solve, and they range from fairly easy to a little bit more involved. So, algebraically, remember, means exactly. That is, no approximations. No approximations are asked for, and if you approximate, you definitely won't have an algebraic solution. You'll have an approximate solution, which is fine if you're allowed to do that or you're interested in doing that, but not in these cases. So the first one, we see that x is inside this log base 3 of x. And so we're going to solve for log base 3 of x by subtracting 4 and dividing by 2. 5 minus 4 is 1, and 1 divided by 2 is 1/2. And now we have log base 3 of x is a half, and the a, b, c equivalent to this is x is 3 raised to the 1/2 power. So that's fairly straightforward. 1/2 power is also known as the square root. Over here, this is already written as a to the b equals c. So if we were to write it in logarithmic form, or equivalently take logs of both sides. Now if you were taking logs of both sides, definitely use ln here because we already have base e term instead of, say, base 4. So we get 2x plus 3 equals ln 4. Subtract 3. And remember, natural log of 4 is some number. Divide by 2, and there is our solution. So these first 2 equations are fairly straightforward. Now the second 2 equations have been ramped up a bit. One nice thing about C here is we can see the variable x appears as part of 2 to the x in both cases. So I'm going to let w equal 2 to the x, and that gives me the equation w squared plus 6w equals 27, which is quadratic w, and can be solved by going to standard form. And from here, you can attempt to factor it, and I believe it does, so we'll take a shot at it. If it didn't, you still have the quadratic formula with a is 1, b is 6, and c is negative 27. And let's see what we get. W and W and a 9 and a 3 and a plus and a minus. And does that work? Yes, it does. So the principal of zero product tells me that either W is 3, setting this factor to 0, or W is negative 9. Now W was just a dummy variable, and so we say 2 to the x is 3 then, or 2 to the x is negative 9. And you might remember that the range of the exponential functions does not include negatives, and so this is probably not going to yield a solution, but let's just go ahead and see what we get. The simplest way to do this is to rewrite each of these. For example, this one, if I rewrote it using the a to the b equals c, I get that x is the log base 2 of 3. Or if you wanted to take logs of both sides, it would take you one more step, and you would get the change of base equivalent of this. And over here, you would have the log base 2 of negative 9, and we're going to reject that. Okay, for this equation over here, again, it's set up nicely for us, and the idea is very much the same, is that I'm going to let w, or u, whatever letter you choose, let u be 4 to the x, and we can see that u plus 6 over u equals 5. And for this equation, we can multiply both sides by our LCD, our only d in fact, and get u squared plus 6 equals 5u, or in standard form, u squared minus 5u plus 6 is 0. And again, this does factor, and if it didn't, we still have the quadratic formula. And I'm going to go with -2 and -3 and check that that does work. Your two solutions are u is 2 and 3. And remember, u was a dummy variable, so we get actually 4 to the x is 2, or 4 to the x is 3. And in a similar fashion, we get that x is log base 4 of 2, or log base 4 of 3. And those are our solutions, and you can check that they both work. Okay, let's look at page 2 here. Here we have some more equations with logarithms in it. And we can see over here, there's a couple ways to handle this one. We might try bringing this log over to this term. I'm going to go ahead and try to write this right-hand side as log base 3 of 3 to the 3. This 3 is that 3. And you'll see in a second why I did this. The reason why I did this is because I'd like to combine these two logarithms. The difference of two logarithms that have the same base is the log of their quotient. And now I have log base 3 of 6 minus x is equal to log base 3 of 27 over x. And one nice thing we have, because logarithms are one-to-one functions, is that 6 minus x must be 27 over x. And you could have achieved this by adding log base 3 of x to both sides. And then these two terms would have combined, giving you a multiplication, which we're about to see here, which is 6 minus x times x is 27, or 6x minus x squared equals 27. 0 is x squared minus 6x plus 27. And let's see, I don't think that factors, in which case a would be 1, b would be -6, and c would be 27. And so we'll get that x is equal to the opposite of b, plus or minus the square root of some stuff, all over 2a. And it's b squared is 36 minus 4 times 27, 4 times 1 times 27. And we get out of this that there, because the discriminant here is less than 0, no real solutions. So that equation died right there on the table. Okay. The next one we get over here on the right is log base 2 of x plus log base 2 of x minus 2 equals 2. And this one we can combine very quickly into log base 2 of x times x minus 2 equals 2. And by converting to an exponential expression, we get x times x minus 2 equals this 2 raised to that 2, or x squared minus 2x equals 4. In standard form. And it doesn't factor, so we have a is 1, b is -2, c is -4. So x is equal to 2 plus or minus the square root of something over 2 times a. B squared is 4 minus, well, I'll go ahead and calculate it. B squared is 4, and 4ac is a -16. So we get 4 minus -16. And if you wanted to clean this up, this would be 1 plus or minus the square root of 5. The square root of 20 is 4 times the square root of 4 times the square root of 5. And 1 plus the square root of 5 works fine up here. 1 minus the square root of 5, however, the square root of 5 is around 2, 2 1/4 maybe. So we have a number that's approximately -1 1/4, and the log of a negative. For example, the log base 2 of 1 minus the square root of 5. Undefined, so I'm going to toss that out. And the other number, I'm going to check that it works fine. So the solution I'm going to stick with is 1 plus the root of 5. That's the only good solution. Okay, this next one is just an expansion. And remember our properties of logarithms. Our first look at this gives us a division, so we can write this as the log of the square root of xy minus the log of z squared. And if you happen to remember that the square root of xy is xy to the 1/2 power, then we can expand each of these as 1/2 the log of xy minus twice the log of z. And again, that multiplication there can be replaced by a log of x plus log of y, so we have 1/2 log of x plus log of y minus 2 log of z. And before I forget, you see there's a mistake in the previous part, which is all of this needs to be multiplied by 1/2. And that would be fine right there. Here we're going in the other direction, and our first step would be to write this as log of x squared minus log of y cubed minus log of z to the 4th. And then this could be written as the log of x squared over y cubed. And then finally this can be written as the log of, if you want to, x squared over y cubed in turn over z to the 4th. And just, if you're wondering if that cleans up slightly, and it does, x squared over y cubed z to the 4th, and that would be fine. And here we have some application problems. The first application problem we're given involves this exponential expression or function, and I'm going to type it in here, so I might as well type it in because I may be using this. So I'm going to type in 250 times e to the minus 0.002 x. And again, how much of the substance is left after 10 weeks? Well, t is measured in days, so 10 weeks, if we were to go to a table, 10 weeks would be 70 days. So after 70 days, it looks like we have 217.34, and let's see, nearest 0.1, so 217.3 grams would be left. How long until there's 200 grams left? Well, one way to do this is if we were to graph it, and I'm going to make my window go from, how about, let's do 365 days. And let's make our y min 0 and our y max what we started with, I believe, 250 grams. It's not, but that's the 0 value, and I'll just look at the graph there. Here's the graph of our decaying function. And we want to know when did it hit 200 grams, and so I'm going to go ahead and draw our horizontal line at level 200. And we see they intersect quite easily. And second calc, intersect, first curve, second curve, guess, skip that. 111.6. On the calculator, we graphed y1 is a of t, and y2 was equal to 200, and the intersection that t, or x in our case, was approximately 111.6. And these were days. Alternatively, we can do this with algebra, which is to write 200 is equal to 250 e to the minus 0.002 t, and solve that for t. So 200 over 250 is e to the minus 0.002 t. The natural log of 200 over 250 is minus 0.002 t. And that tells us that t is the natural log of 200 over 250 over minus 0.002. And that should turn out to be pretty much the same number as this one, so let's check. So the natural log of 200 divided by 250 divided by minus 0.002, 111.57, so to the nearest tenth would be 111.6 days. Okay. Now the half-life is the amount of time until half the initial amount remains. And we started with 250 grams. You can check that when t is 0, we get 250. So we have 125 is equal to 250 e to the minus 0.002 t. And we'd solve that for t in the same way that we solved this for t. Or maybe a little bit faster since we have this thing already graphed. Change our y2 to 125, and hopefully we'll get a hit. We may have to extend our window a bit. Let's see, and they may intersect. Let's check. Yes, yes, yes. Let's see if we get an intersection. 346 just inside the year. Nearest tenth, it'd be 346.6. 346.6 days. Okay. All right, here's a slightly more complicated picture. And again, we have a function n of t, where n represents the number of fish after t weeks in this case. And so I'm going to go ahead and type this one in. So I'm going to type in, we have 1200 divided by 1 plus 47 times e to the minus 0.165x, again, close the exponent and close the denominator. And the first question is, how many trout were initially placed in the lake? Well, we go to a table and we type in 0. We see there was 25. So n of 0 is 25 fish, or trout, or whatever they are. And after 60 days, and again, remember, t is measured in weeks, so we would type in 60 divided by 7. We get there's around, let's say 97. And of 60 over 7 is approximately 97 fish. When will the population reach 500? And again, we'll do this both graphically and algebraically. To do it graphically, we would draw a horizontal line at 500, and we've got a fairly big window here. I'm going to go with 52 weeks, and I'm going to go zoom 0. Let's check and see how good of a picture we get. There's our fish population coming up, and notice it tapering off, and we see a nice intersection there. So we have an intersection at 21.3, and this would be t is approximately 21.3, and again here we're measuring time in weeks. And if you were to do it algebraically, we'll look at that in a second. The maximum number of fish the lake would support, well, we're looking for what happens to the number of fish as time gets larger and larger. And if we went to a table of values and typed in successfully larger values, 10, 100 weeks, 1,000 weeks, you can see already that the stock number of fish in the lake has already flattened out at 1,200. And from our graph, you can see that the rise in population starts to flatten out. And there is a horizontal asymptote up here at level 1,200. And just experimentally, we can see that as time goes on, we end up with more closer and closer populations to 1,200. So the maximum number of fish would be 1,200 fish. Now to solve this C4C algebraically, we would be trying to set 500 equal to 1,200 over 1 plus 47 e to the minus 0.165 t and solve that for t. You can cross multiply and you would get 500 plus, let's see what 500 times 47 is. 23,500. 23,500 e to the minus 0.165 t is equal to 1,200. Subtract 500 from both sides, and you get 700, and divide both sides by 23,500, and you get e to the minus 0.165 t is equal to this, or minus 0.165 t is the natural log of this quantity, 7 over 235. And you finally get that t, if I can fit it in here, is equal to the natural log of 7 over 235 itself divided by minus 0.165. And we should find that that's very much the 21.3 weeks we had before. So let's just check this. Natural log of 7 divided by 235 divided by minus 0.165. 21.29500, which is fairly close to 29.3. Good enough. Okay. The next page in our problems is a cooling problem. And it looks like there's some strange typo-ness in this. We have a function h of t, which gives the temperature of the coffee in degrees Fahrenheit t minutes after it's poured, and this is relating to Newton's law of cooling, and we have a picture here where basically the room temperature in this case is 72, and you can check that the limit of the function is 72, and we start off at a certain temperature, and we'll find that in a second. And the coffee is cooling down like that, where the room is held at a constant temperature. And this would be our h, and this would be our time. And now, h of 10, I'm going to go ahead and type this in. Again, it's useful to have it in for various reasons. So we have 72 plus 68 times e to the minus 0.23. Minus 0.23x. Again, we can't use t. Okay, and first thing we want to find is h of 10. So we might as well go to a table. Type in 10 and see what we get. We get 78.818. And I guess to the nearest, we'll go to the nearest degree. So that'd be 79. H of 10 is approximately 79. And it asks us what that means. Well, 10 minutes is what the 10 refers to. There's our t. 10 minutes after pouring. The coffee's temperature, and that's what h of t is. The coffee is at 79 degrees Fahrenheit. Now, when will it reach 75? For that, we want to know when is this quantity 75. So algebraically, we'd be looking at 75 is 72 plus 68 e to the minus 0.23 t. We can solve that algebraically, or we could use our calculator. And our graph, let's see our window, 52 minutes. Let's go with 120 minutes, that's 2 hours. And we know that the lowest temperature would be probably a lot higher than 0, but we'll go between 0 and the starting, say, 200 degrees. Okay, and let's see what kind of graph we get. Wow, okay, it's flattened out quite rapidly. You can see the temperature comes down quite quickly. And I'll go ahead and draw a horizontal line at level 75. And let's see. I believe there's an intersection in there. You might not be able to see it, but let's go ahead and see what our calculator will do. It has an intersection where we expect, and we could, this is 13 point, let's make it 13.6. It looks like minutes. At t is approximately 13.6, and this would be minutes. Okay, we could zoom in on this. There's our constant temperature 75, and was that? Went from 45 to 75, 49 to 79. We've zoomed in quite a bit there. Well, all right, enough of that. If the coffee will eventually reach the temperature of its environment, what temperature is its environment? Well, I went and wrote 72 there because I know how this shapes up. But let's go ahead and look at this function and look at it for increasingly larger values of our time. And this is not proving anything. But what we see is, and we could do this on shorter intervals, and it might even look better if we were to say, go to an automatic table that started at 0 and increased by 1 each time. Now, if you look at the temperatures on the right, the initial temperature was 140 degrees at time 0. And you can see the temperature is cooling off here. As we scroll down, it's at 77 degrees after 11 minutes, 76 degrees after 12 minutes. And you can see the temperature doesn't seem to be getting any lower than 72. In fact, if you look at it, it just hits 72 and sticks there almost. You can see the number of zeros. The number of zeros here is increasing, but we're not going down to 71. Another 0, and you can see going further and further and further. So out here at 100 minutes or 102 minutes, we're almost exactly 72 degrees. Okay? And I would say 72 degrees Fahrenheit. Okay? By looking at larger and larger values. Now that's the free response section of these two tests. These are two tests melded together, and these are a bunch of short answer multiple choice questions. The first one asks, which of these functions is one-to-one? They're all functions, and one-to-oneness is passing the horizontal line test. And if we were to look at the graphs of these, for example, this one would have a graph which is a parabola and that fails a horizontal line test. And this one we know it's end behavior. It's a positive leading coefficient, and it's an even degree function. So its end behavior would be up, up. That would also fail the horizontal line test. So if you look at y equal x cubed, you could look at each of these individually. But x to the third power, zoom 6, you can see it seems to pass our horizontal line test. Now, whether there's a little up and down in there, we're not positive. Or you could just verify that you happen to know this has an inverse, namely the cube root. And so the answer here would be B. Okay. This next one asks us if log, well, what's the base here? The base we don't see is base 10. If log base 10 of x to the x is x. Well, we could check. We could write this as x times log base 10 of x. Is that equal to x? Well, these two are equal only if log of x is 1, and that's generally not true. So unless x is 10 itself, which would make this 1, unless x is that number, there's no specifications of that, this is false. Here we're asking whether e to the log of x is x, and that's also false. What is true is that e to the ln of x is equal to x. In general, the identities we're referring to is a raised to the log base a of x is x, and the log base a of a to the x is equal to x. These two are identities that just reiterate that f of f inverse of x should be x, and f inverse of f of x should be x. And then here, e to the ln is 0. Well, the natural log of 0 is undefined. So we get nothing out of this. And the problem here is that the right-hand side is defined, but the left-hand side is not. So this would also be false. Okay, it says the right pattern, but it fails in the execution. Approximate the log base square root of 2 of the square root of 3 to the nearest thousandth. Well, here we use the change of base formula, and we'll go to, say, natural log. So this is equal to the ln of the square root of 3 over the ln of the square root of 2, and we will just do this in our calculator. So the natural log of the square root of 3, close the square root, close the natural log, divided by the natural log of the square root of 2. And to the nearest thousandth, it's 1.585. Which of these functions will pass the horizontal line test, and so we could graph them individually, or we could just look to see if any of them fail the horizontal line test. For example, these 2 points are at the same y level, but they have different x values, so they fail the horizontal line test, as do these first 2 points here. And you can see none of these have the same y value, so that graph would pass the horizontal line test. Which of the next set of pictures is a one-to-one function? Now remember, to be a one-to-one function, you first have to be a function. So C, although it passes the horizontal line test, is not acceptable. This one is a function, but it's not one-to-one. This is not a function. This one is a function, but it's not one-to-one. And the only answer here is A, which looks to be some sort of logarithmic graph. 13 asks us the same question. Which function has an inverse? Okay. Passing the horizontal line test, being a one-to-one function, and having an inverse are all the same thing. Well, the graph of f of x equals 2 would be a horizontal line, and so this guy doesn't have an inverse. The graph of 2x is an oblique line, which looks something like this. And it passes through 1, 2. And that does have an inverse, namely 1/2 x. This is a parabola, which is a function, but unfortunately fails the horizontal line test. So the answer would be B. Now the domain of 2 to the x plus 1, 2 to the x plus 1 is the graph of 2 to the x. There's 2 to the x that's been shifted up by 1 unit. So what was the horizontal asymptote at y equals 0 is now the horizontal asymptote at y equals 1. And what was the y-intercept at 0, 1 is now the y-intercept at 0, 2. And so the graph of 2 to the x plus 1 would be this one. And if all we want from this is the domain, well, the domain is the same as the domain, namely all real numbers, or minus infinity to plus infinity. The range of it, on the other hand, we can see from this is, well, it was 0 to infinity for 2 to the x. It's been shifted up by 1, so it's 1 to infinity. Or the set of all y such that y is greater than 1. Now again, we see another kind of situation. We have a picture of log base 2 of x, which goes through 0, 1. This is log base 2 of x. And by the way, that's the reflection of 2 to the x across the line y equals x. So the domain and range of 2 to the x and log base 2 of x are exchanges of each other. Now this one has been shifted to the right by 1 unit. So what was the vertical asymptote here now becomes the vertical asymptote here. What was the x-intercept here becomes the x-intercept here. And so we get the graph of log base 2 of the quantity x plus 1. And we have the domain of this is 1 to infinity, and the range is all real numbers, or minus infinity to infinity. Let's see what else we have. Okay. Here we have matching the expressions here with supposedly equivalent expressions on the right-hand side. So let's check. The first one should be pretty straightforward. This can be written as the log of x plus the log of y, straight up application of one of our properties of logarithms. And we see right off the bat that that's a. This one is the log of x minus the log of y. And again, pretty easy. G. And this would be y times the log of x. And let's see if we see a y log x is a c. Now, log of x over log of y, the best thing I can say is that that's a change of base, and it would be log base y of x. let's see if we see log base y of x, and we see e there. Remember, expanding, contracting, that is, an identity goes from left to right as well as from right to left. So don't just get used to seeing something like this. The log base y of x equals the log of x over the log of y. In this direction, that's true, but sometimes you may want to go back the other direction, as in this case. Log of x times log of y. Well, if we think of it as a case like this, then certainly we could write this as the log of y raised to the log of x. Or, if we saw this as being the exponent that had been pulled out, the log of x raised to the log of y. So let's see if we get either of those. The log of y raised to the log of x, we get that one right there, so D. Now 19 is an example of our identity from the previous page. I don't know if you can see this, but this is x raised to the log base x, and that's key there. And so that's just y, and let's see, that's j. The log base x of x, and again, implicitly, there's a 1 there. X is x to the first power, and that should equal 1. And that's k. Log base x of 1, well, that's the log base x of x to the 0, and that should be 0, and we see that that's L. And the log base x of x to the y, that's y again. Again, this is that identity, and that would be j. And the log base x of 0 is undefined. Our logarithms have strictly real domains and ranges, and for that we need to have the inputs of the logarithms be greater than 0. Okay, so this last set here has us looking at the graph of a function, verifying that a passive vertical line tested is a function. Explain why f inverse exists. Well, here's a function, and if its graph passes the horizontal line test, which it just does right here, is the only place it might be close, but the dark circle is in, the open circle's out, so there is no situation where a horizontal line touches the graph twice. So because it passes the horizontal line test, or the graph of f passes the horizontal line test. Now to sketch the graph of the inverse function, we just need to reflect the graph across the line y equals x. And the line y equals x is that line. Goes through 0, 0, 1, 1, etc. Here's y equals x. And so what we're going to do is take each point. For example, since it's made up of linear pieces, we'll take each point in turn. So -1, -2 would go to -2, -1. And we'd go right there. -2, 1 would go to 1, -2. Right there. And finally, 1, 2, 3, 4, 5, -5, +2 would go to +2, -5, and that would be an open circle there. And so here would be one reflection. And you can see pairwise, this pair are reflections of each other. Now this other one's very easy. We're just going to reflect across the line y equals x, and we get something like this. So there's a graph of f inverse of x on the same axes. Okay. Find the domain of f inverse. We could look at the pencil graph of f inverse and look at the x's on it. Its domain would be starting at -2, and it would start at -2, including -2, and go up to 2, and that would continue because you can see that projecting onto the x-axis, we cover everything out to plus infinity. So from -2 to positive infinity. The range would be from -5 up to, and it goes up, up, up until it hits -1, and then it stops. There's a gap, and then it picks up again at +1 and goes on to plus infinity. And these, by the way, would be the range and domain of f itself. If you were to look at the domain of the original dart graph, you should see that it is from -5 to -1 and from 1 to plus infinity. F of 1, looking at the dart graph, we see when x is 1, we get 2. F inverse of 1, we look at the pencil graph, and we can see when x is 1, we get -2. F of 1, well, that's f of 2 by this, and f of 2, the black graph, is 3. F inverse of 1, we know, according to this, is f inverse of -2. And if we look at x equals -2 on the pencil graph, we see that it's equal to -1. And f of f inverse of 1, it should be 1. And let's just verify that 1 is in the domain of f inverse, and 1 is in the domain of f inverse, and 1 would go to -2 under f inverse, and -2 would go back to 1 by f. And so that works out. Now these last two questions are bonuses, and they're just harder than usual problems, and there's not going to be any bonuses in your test, but if I find a clean piece of paper, I'll show you how we can do these problems. Okay, let's start with the first one. Solve log of x plus ln of x equals 2. The first problem here is that we have two different bases. Normally this would be fairly easy, but the base in the first case is 10, the base in the second case is e. So I would recommend changing them to the same base. And for example, we could leave this one alone and change this to base 10. So it would look like log of x plus, and now this is log of x over log of e. And now from the point of view of x, we can see that log of x appears twice, and these two terms are like. 1 plus 1 over log of e is 2. And so the log of x is equal to 2 over this. Divide both sides by whatever this number is, and we'll clean this up in a second. And I'm going to go ahead and clean this up by multiplying top and bottom by the log of e. And the log of e is some number. The power 10 needs to be raised to get e, around 2.7 and some change. So we get 2 log e over log e plus 1. And that is what log of x is equal to. And then our last step would be to simply convert this to an exponential statement, which is that x is 10 raised to this power. 2 log e over log e plus 1. And this would be our solution for x. Now the second problem, prove that log base a of b is the log base b of a to the negative first power. Well, let's try that one. Let's see. So again, it looks like a change of base issue here. So we're going to start with the log base a of b, and we're going to convert it to base b logarithms. And we know that this is the log base b of b over the log base b of a. Again, this is our old base we see here. This is our old argument we see here, and our new base is base b. And you know the log base b of b to the first power is 1. And then we know that the definition of the negative first power is that it's reciprocal. So we have log base b of a's reciprocal is log base a of b. And the last one is one of these ones where if you've seen it once or twice, then this trick is fairly routine. 9 to the x plus 3 to the x plus 1 equals 1. The idea here is to see that 9 to the x is 3 to the x squared, and 3 to the x plus 1 is 3 times 3 to the x. And we have w squared plus 3w minus 1 is 0. And so our solution for w, our dummy variable, is negative 3 plus or minus the square root of some things, all over 2a. 9 minus 4 times 1 times negative 1 is 13. And so we have 3 to the x is negative 3 plus or minus square root of 13 over 2. And so x would equal the log base 3 of negative 3 plus or minus the square root of 13 all over 2. And negative 3 minus the square root of 13 over 2 is a negative number whose logarithm is not real. So the log base 3 of negative 3 plus the root 13 over 2 is our only solution to that one. And those are the bonus problems. And good luck on your test.